Welcome to my YouTube channel Thermal Engineering. In last video we have studied governing equation for rectangular fin. So for this fin we had differential equation. So today for the differential equation said here there are three cases. Out of that, case 1 we are going to see, that is heat flow for an infinitely long fin. So here let governing equation for rectangular fin that already we have done, that is d square theta divided by dx square minus m square theta is equal to 0. For this we will have general solution, and in that solution there will be C1 and C2 constants. We have to find values or expressions for C1 and C2, and then we have to find equation for heat flow for an infinitely long fin. So let us here consider long fin with the help of diagram. So this is a long fin with length L. Here we have to obtain temperature distribution for this fin. So we will have this vertical axis temperature and horizontal axis distance x. So here there will be two cases for the, so here this will be temperature profile. So in this case here at x is equal to 0 and here x is equal to L, these will be two boundary conditions. So at x is equal to 0, temperature at the base of the fin will be T0, and at x is equal to L, temperature means at the end of fin, that will be T infinity. So here now we will have first of all boundary conditions. So we will consider boundary conditions. Boundary conditions. Here will be first condition at x is equal to 0, temperature T0. So here theta will be equal to theta 0. Now what is theta 0 and what is theta? So here in this diagram we will see. So theta 0 means difference between the temperatures. So here this side, this will be theta 0 at x is equal to 0 distance, means at the base. So this will be difference between T0 and T infinity, that is theta 0. And this side means at the end, theta will be T minus T infinity, means in this case at the end temperature T infinity is equal to T. So that's why it comes 0 at the right hand side. So this is the first boundary condition at the base, and at the tip of fin, means at x is equal to L, L tends to infinity, theta will be 0, because here T is equal to T infinity temperature. So in this case, theta, that is T minus T infinity, that equal to 0. Now we have here general equation or general solution that already we have derived in last video, that is theta is equal to C1 into e raised to mx plus C2 into e raised to minus mx. So this we will say as equation number 1, that is general solution. General solution. Now applying first boundary condition. Apply first boundary condition. We will have here equation theta in this case is equal to 0. Theta 0 is equal to C1 into e raised to m. X value at first boundary condition is 0, m into 0 plus C2 into e raised to minus m into 0. By solving this equation here, C1, m into 0 means 0, e raised to 0, that will be equal to 1 plus C2 into m into 0 again 0, e raised to 0, that will be again 1. So here we will have here equation theta is equal to 0, theta 0 is equal to C1 plus C2. This we will get, this we will say as a equation number 2. Now this equation 2 we get by application of boundary condition first, means for these values. Similarly, we will do the work for boundary condition 2. So boundary condition 2. So boundary condition 2 is what? X is equal to L and theta is equal to 0. So for boundary condition 2, here the equation, that is theta is equal to this equation. In this equation we will put the values. So theta is equal to 0 into is equal to C1 into e raised to m into x value. Now x value we will take here at the end, that is infinity. So m into infinity plus C2 into e raised to minus m into infinity. So further simplification, we will have here C1 into e raised to m infinity plus this C2. Now e raised to minus m infinity we can write in this way, C2 divided by e raised to m infinity. So here we can have this. So here we will find here C1 e raised to infinity m plus value of this C2 upon e raised to infinity m, that will become 0. So here left side is 0, right side is 0. So finally it will produce C1 is equal to equation is 3, value of C1. Now equation 2, here theta 0 is equal to C1 plus C2. So putting this value in equation 2, putting 3 in 2, we can get C2 theta 0 is equal to 0 plus C2. So we will have here theta 0 is equal to C2. Now further, now we will have here these values C1 and C2. So next step is putting values of C1 and C2. Okay, this we will say as a equation number 4. In equation 1. So equation 1, in that, what is equation 1? This is equation 1. So we will have here theta is equal to C1 is equal to 0 into e raised to mx plus C2 is theta 0 e raised minus mx. Now this term will become 0. So theta will be equal to theta 0 into e raised to minus mx. So further simplification of this will be what? Theta upon theta 0 is equal to e raised to minus mx. So we will have here this equation, say equation number 5. Now this is temperature distribution. This equation is temperature distribution along fin, that is infinitely long fin. This can be written in this way also, that is t minus t infinity for theta, already we have seen in the figure, divided by for theta 0 we had t 0 minus t infinity is equal to e raised to minus mx. Say equation number 6. So this was a first part, that is part A, boundary condition. Now part B. Here we will have heat flow rate. For this now we will have the equation. So take theta is equal to theta 0 into e raised to minus mx. That is this above equation. Okay. So here theta is equal to, for theta 0, we can take this t0 minus t infinity. So t0 minus t infinity into e raised to minus mx. Now differentiate this equation with respect to x. So differentiating this equation, differentiate with respect to x. So for that we will have here differentiation, that is d theta by dx is equal to t0 minus t infinity. This will come as it is out of the bracket here. Differentiation of e raised to minus mx, that will be e raised to minus mx into differentiation of minus mx, that will be minus m into differentiation of x will be 1. So here we will have the equation, that is t0 minus t infinity, this sign m into e raised to minus mx, and this minus sign we will have here. So let us have this equation. We will write this equation as equation number 7. Now, as per Fourier's law, Q means heat flow rate, that is equal to K into A into d theta by dx at x is equal to 0, means at the base of the fin. So in this case now, here Q is equal to minus K into A into, for d theta by dx we have this expression, so we can write this in the bracket. At x is equal to 0. So next, now what we have to put? We have to put value of x is equal to 0. So next, this minus sign will become plus. So K into A, this M will come outside the bracket, T0 minus T infinity into e raised to minus M, value of x that we have to write as a 0. So further, K into A into M, T 0 minus T infinity, e raised to minus M into 0 means 0, e raised to 0 means 1. So here we will have next step. Now as we know m square is equal to hp by ka, means m will be what? Square root of hp by ka. So now we can substitute this hp by ka under the square root for this m. in the next step. So next step is here. Q is equal to K into A. For M we have HP by KA into T0 minus T infinity. Okay, so here this KA will get cancelled to this square root of KA will get cancelled with this KA and will remain here. That will come, that is under the square root KA, and this already HP into T naught minus T infinity. So this will be next equation. So this is the equation, that is the heat flow for long fin. This we will say as a equation number 8. Now part C, heat flow rate. Heat flow rate by convection. At base of fin. So that will be QC. This can be taken or written as integration of 0 to infinity, and we know that for the convection heat transfer equation is HP dx into T minus T infinity. From case 1, this in last video we have seen. So here now 0 to infinity HP dx. Now in this case T minus T infinity, we have taken T equal to T0 in the boundary condition at the base. So this equation will be written as in this way: T minus T infinity into e raised to minus mx. Next step, here HP T naught or T0, this will come outside of the integration sign. In the integration there will be e raised to minus mx into dx. So now next step, HP T naught minus T infinity, here integration of e raised to minus mx, that will be minus 1 upon m into e raised to minus mx. These are the integration limits, lower limit, upper limit. Now I will put the limits in the equation and we will modify. So here next HP T0 minus T infinity here minus 1 upon m, here in this bracket 0 minus 1. How it came? Here e raised to first upper limit at the x is infinity, so e raised to minus infinity, that will become 0, and lower limit e raised to minus m into value of x 0, this total will become 0, e raised to 0, means 1. So upper limit minus lower limit value. So finally we will have here HP T naught divided by M. Now this minus and this minus will become plus. So here minus sign will vanish. Now M is square root of HP by KE. So further next HP into this temperature difference at the place of M we know that it is HP by KE. So by simplification of this we will have here this HP will get to this HP. This is square root of HP and this is HP. So here square root of HP will come into this temperature difference and this 1 upon KE. So it will come here at the numerator. So finally QC will be K into A into HP T naught minus T infinity. This will be the equation for heat flow rate by convection. Say equation number 9. So here this equation will be same as of equation for infinite long fin heat flow, equation number 8 and equation number 9. Both are same. So that's why from 8 and 9 Q is equal to QC. So for infinite long fin, heat flow rate is equal to heat flow rate by convection. Both are same. So in this way we have seen here in this case heat flow for rectangular fin. That is case 1. Heat flow for an infinitely long fin. So for this differential equation solution we got, and after finding C1 C2 value finally we obtain this equation, heat flow rate Q is equal to QC. So subscribe the channel for heat and mass transfer video sessions. Thank you.